So I'll go ahead and start, but don't hesitate to stop me. I probably in today's, what I have here, I have a PowerPoint and then I have a Jupyter notebook to work through on some examples. So the PowerPoint is really meant essentially to give you background about who we are and how we came to be involved with AgGateway, and in effect, what we're sort of seeking what is our proper role in AgGateway. And I think one of the things that we're hoping is a proper role is an educational role. It's a thing that a university hopefully does well. So the plan really is day one, this background, and then a little overview of the curriculum that we're going to go through. We'll start really slow. I mean, this is meant to be a very basic course on Python, very basic. We will, though, hopefully get to some more sophisticated things at the end of the course where we're looking at some real data that we took on Krogmeyer farms that our students have analyzed. These are primarily data of tracks of machines that operate on fields as they're doing a wheat harvest in Colorado. So we'll experiment with that, and day two we'll do a lot more with that. Then we'll do a little bit of overview of data science, and then the Python basics, and then day two we'll continue that. After my talk, Andrew Balmos will speak about an experiment that he's designed in the area of sort of wireless in fields. And then tomorrow, Aaron Alt will speak about blockchain and smart contracts, or Oblivious smart contracts. So to start with, what's the OATS Center? So it stands for Open Ag Technology and Systems, and we had to have a mission statement, so we came up with this one. It works to enhance ag innovation in the areas of sensing, control, logistics, analytics, data management, and it really tries to do these activities in the context of open source. If you look at my background, I'm really a signal processing person. I study wireless communications and signal processing, and so where I came at from this is all of those sort of electrical engineering subjects, sensing, control, communications. Aaron Alt, who works with me, is more of a computer engineer, a computer scientist, so he comes at it more from computing systems and really a lot of stuff, cloud sorts of things and APIs. This is also how we came to be involved with AgGateway, because AgGateway supported our proposal, and we have been working to try to support AgGateway's mission and mutually collaborate, really. It's very important to the foundation that this sort of thing be done, because the foundation was set up as a transitional research funding organization. In other words, it was meant to take research results from National Science Foundation or from NIFA and translate them more to practice. It was funded by the 2014 Farm Bill, I believe, to the tune of several $100 million. They did not give me several $100 million, and that's probably a good thing. I probably would have wasted it, sorry. But I'm working on spending my $2 million. So at any rate, the full value of data, the issues that we came up with, the full value of data is only realized when it's integrated from multiple context-rich sources and ways to adhere to the trust requirements of its owners. I don't think there's too much to disagree with here, but we want to point out that really the rapid rise of this effort in data-driven agriculture has left many stakeholders behind. So they're not, and the data and algorithms are not publicly funded food and ag research are not easily obtainable. This is one of the things that has come up to us various times, people coming to us wanting to get Purdue data off Purdue research farms. All the Big Ten and land-grant universities operate large research farms, thousands and thousands of acres, running many, many trials, and it turns out that it's difficult to get the data. For the most part, it's difficult to get the data because it's just manually a problem. People are storing it on zip drives and on systems that are not connected to the internet, and it's siloized, just like it's sometimes siloized in industry. So it was that observation that really led us to say, we got the same problem in the research farms at Purdue as people have in the ag industry. Many stakeholders are short of the proper data analytics skills necessary to thrive. And so the university has a research and a teaching mission that should help to address that. And then we would also say, in this I'm not pointing really at the ag industry as much as I'm pointing at the university. It's somewhat shocking sometimes how far behind the state of the art the university's research systems are when it comes to data and sharing data and curating data and that kind of thing. So it was our notion here that what could help solve this was open source, open standards, and market forces that would help to move things forward. If you look carefully, that's exactly the mission of AgGateway as well. AgGateway focused more on industry, we're focused more on university. Here's a slide that summarizes in a way what the mission of that research project was to be. It was really to design data APIs for sharing data between research groups at Purdue and do it in the open, not in the closed doors, but really our philosophy is that data exchange APIs are not something you easily define abstractly. It's almost too complicated when you start to try to think abstractly about this thing. So you think practically about particular data sharing activities that you want to do, and you design it in the open, you publish it in the open source, and when you publish it in that way, people can also take your work and change it if they don't like it. So another aspect of it was the foundation wants this activity to persist beyond the funding 3 years that they gave us. So in order to do that, we set up an industry consortium. These are the faculty members that are in the industry consortium. I won't belabor this too long, except to point out that what you see here is representation from engineering, from ag and bioengineering, from agronomy, from food science, ag and bio, me. David Love does communications. So we've got people here that are covering most of the pain points that you see in the data space in agriculture. One of them is the sharing of data. The other one is the fact that we don't have great connectivity out in rural areas. So food science again, and going forward, statistics, and so on. The center also works with a number of other centers at Purdue, so I won't belabor that point too much, except to say that we have very good connection to the Cybersecurity Center at Purdue, which really focuses completely on cybersecurity, and that, of course, is a concern from time to time in this space as well. Other important collaborations, Joint Transportation Research Program. So we do a fair bit of work at the interface between farm machines on roads and farm machines in fields, which is an area that honestly has been very much left out in transportation research. So when we made a report, this slide is kind of really the slide that I made for the foundation to try to encourage them to send their second year's money. We had 3 goals in the first year, really. The creation of open source community anchors, the design of educational experiences and materials, the development of open source hardware and software. And so I'll now go through a little bit of the things that we've done in all those 3 areas. So open source community anchors. We've held a number of OATS events. We hold an event every spring at Rosemont at the Big Ten Conference Center. And Wendy's been there twice now, and we hope that she'll be able to come again, and maybe a few more of you might be able to come. I mean, one thing that we're brainstorming, it's really just a crazy idea at the moment, but the idea might be to have a second day, which is really a hacking day or an API design day, something like that, where we bring in students and bring some of you together with them, and we figure out some of this stuff and just work out some examples and some proof of concepts. I think the foundation would be very interested in that if AgGateway is interested in that, and the members of AgGateway are interested in that. In addition, we've been going to AgGateway meetings for quite a while, and here we are at the annual meeting, and this idea of an educational session kind of grew out of those. So one of the things you're going to need to tell us is this useful to you? Because it's my intention to teach you at the end of this something about Python as a coding language, and maybe you don't want to know. Although, I guess if you really didn't want to know, you probably wouldn't have come to this. It's probably the very best single language to learn if you're not sort of if you're not going to be a computer scientist. I don't know if Aaron agrees with that, but he'd say JavaScript. Yeah, that's what he would say. I should have known. But at any rate, many would say Python. Google does a lot of work with Python. It's an open source thing. At the university, we typically use a lot of MATLAB. And there's one major problem with MATLAB. Does anyone know what that is? Yeah, it just costs a lot of money. It does not cost us a lot of money because they give it to the university in order to get everyone addicted. And then when you go to company, you ask your employer to buy it, and MATLAB says fork over 200 grand or something. I mean, it is extraordinarily expensive. And so that's the reason for doing Python. Python has a community of developers out there, and a lot of them have been working on essentially working around MATLAB. So Python has a lot of MATLAB constructs in it. It works a lot like MATLAB, and you'll see some of that today. We've also been working in this area called Trellis, which is really OATA for food safety audits. When Aaron speaks tomorrow, he'll speak a little more about that. And then a lot of other activities with Midwest Big Data Hub, which is it's centered at the University of Illinois, ASABE. There's a group called Gathering for Open Ag Technology, which is another open source group in agriculture. And we've been saying that we are the OATS for goats. Hasn't quite caught on like I hoped, but hopefully it will eventually. Open educational materials, experiences, and so on. We have IsoBlue 2.0, which is an open source telematics unit that online you can see how to build them. We have software there as well. There's a fair bit of development going on in here, mostly because it seems to fit now with some things the NSF is wanting to do as far as putting some research funding behind solving rural broadband issues. And so it's a platform that we can experiment with telematics and with machine connections and sensors. And we're trying to make it into a platform that's really much broader than, the normal thing. I guess maybe I should back up here. If all you really want is the data off the CAN bus on your tractor, and that's all you really want, you don't need us. You don't need IsoBlue. In fact, it would be dumb as heck, I think, to build an IsoBlue if that was your only goal. Industry has figured out how to do that. They've got it done quite well. Climate will put a puck in your tractor. John Deere has my John Deere. Case New Holland has their way of doing it. This problem is essentially solved, except that the systems don't work as well together as they should, but the telematics part of it's pretty good, except that, of course, we don't have good connectivity out in rural areas, and there isn't a whole lot they can do about that. But if you're wanting to experiment with adding new things to it, like I want to make a LoRaWAN gateway out of an IsoBlue, or I want to add some sort of communications protocol that talks to sensors in the dirt that isn't a standard or anything like that, then you need a platform you can actually program on, and you can change, and you can do things. And you can't do that with Climate's puck. So it's very much a research thing, or for beta user type people. And then we've got some grants that are going right now that are sort of trying to develop these data science tools for undergraduates, and so that's partly the material that I brought to you. Aaron will speak more about this open source software and hardware. Trellis is one of the more active things going on right now. It's really OATA branded for food safety audit sharing. The OATS Center has a number of new members: Arva Intelligence, Salimtech, Climate Corp. Arva and Salimtech are small startups based in the research park at Purdue, and we're quite proud that they were interested enough to join because that's the kind of thing we really want to be doing, is helping startups to get going. We're working with a large program called NSF Power. Power stands for Platforms for Advanced Wireless Research, and this is a proposal, or a grant actually, led by NC State, and NC State is going to build half a dozen or a dozen IsoBlues and implement them in their test bed. We're also working with UPenn on an NSF ERC called Center for Internet of Things for Precision Agriculture. We're working with the Indiana Economic Development Corporation on various test beds in the West Lafayette area that are really focused more on testing of communications technologies, but also has this OATA back end into it. So it's interesting that there's a lot of activity going on there right now. The NSF also recently came out with a big call for proposals for AI institutes, or artificial intelligence institutes. And I believe they say they're going to fund 5 of them, and one of them is in agriculture. So when I first started working in this area with Aaron and Dennis Buckmaster, I wrote a proposal to fund an ERC to the NSF. ERC is like the holy grail of proposals. It's called Engineering Research Center. It gives you 10 years of funding. So if I got 10 years of funding now, I can, I'll be retiring. I'll leave Aaron and Andrew, homeless and whatever, but I'll be gone. My problems will be over. But I wrote this thing 6, 7 years ago, and the NSF's answer to that was, this is really not interesting at all. We don't want to fund anything in agriculture. So you can see, in a certain sense, in a small way, our agitating, your agitating, and the successes that the industry has had has raised the level of interest enough that an organization that typically does not fund agricultural research is willing to do it. That's kind of interesting. The research that goes on in OATS is really cloud computing, machine learning, and so forth, and a lot of this stuff, and I'm going to move a little faster. To come back really to kind of our roots here. Our work is animated, and this is an old graphic that Aaron created a long time ago, about the trouble a farmer has in the middle of the data problem that they see. And the interesting thing is, of course, we had a wonderful talk yesterday. And sadly, happily, it's a wonderful talk, and it was wonderful to meet that guy, Jake, but sadly, it's still not solved. And Jake's all green. You'd think that his problems were solved, so apparently not. I found that fascinating. And at any rate, it really, it animates what we do because we feel much closer to farmers than we do to companies for the most part. So we hope to be an honest broker there. And so this was the old idea here that managing your data in the middle of it, where you're the one in charge of every bit, holding it in zip drives in various places, tends to wear the farmer out, and he gets all discouraged there. And then finally, if somebody comes up with a way for the data to be shared at his autonomously or automatically under his control, life is a better thing. So our work is animated by this need to help farmers. I think ultimately AgGateway is also animated by the need to help farmers, but it's helping them through its members. And anybody smart and wants to make money and survive in this space obviously needs to keep customers in mind. And we need to thank Jake for that nice reminder that we should do that. He's not here right now. I think he actually had to go work. That's the problem with farmers. Aaron's here today, but he's going to be gone as soon as he can get. So in our work, you'll see actual farm data. We focus really on farm data. We don't do a lot of simulation. I wish we could do a lot of simulation, but we really don't. So actual data tracks, trying to do grain traceability by keeping track of these tracks, looking at the machine data on the CAN bus and trying to do clustering of that data by the types of things that are going on, trying to put that on maps in order to find things that are unusual going on. So we're looking here not so much at the agronomic thing here, but how is the machine working? One of the things that's motivating this particular line of work is autonomy. How does autonomy roll out in agriculture? And I would wager, or I would claim, that the problem of driving a combine is harder than driving a Honda Fit. Even though the cost of screwing up in a Honda Fit is very high, it's an accident, maybe somebody dies, that job of doing it has less things to worry about, at least, than operating a combine or operating a planter. And so there are efforts to make that autonomous. There's a lot of problems to solve. And the large industry that's solving many of these, the Googles and the Ubers and stuff, are not looking at this problem. We need to come up with tools that help us to log data and automatically clip that data and create learning data sets autonomously or automatically with less human effort. All right, again, thanks to our sponsors, and thanks especially to AgGateway. AgGateway has been one of the most important sponsors. not in dollar sense really, but in opportunity sense, and the chance to talk to you and the chance to have our work have some meaning. Okay, so now I'll skip. Is there any questions about any of that? Don't hesitate to just yell out if you're disgusted or need to stop, or but there will be a test. That doesn't really scare anybody, does it? Okay, so today, after I'm done, Andrew will speak about networking research for Ag IoT, and then tomorrow Aaron will speak, and we'll continue on here. So data science is a field of study. So what is data? Well, there's a whole lot of different definitions. That's one of the big problems with the whole thing. You've got this notion of information. You've got a notion of data. You've got a notion of analog data, digital data, knowledge, measurements, false belief. It's all hooked in there together. In a certain sense, some people kind of think of information as the state of the thing you're trying to ascertain, but you have data which tells you about it, and the data is typically noisy. Sometimes it's corrupted with kind of perturbation noise, what we would call thermal noise. A typical sensor has noise of this nature on it. If you're measuring the yield in a combine, the way that that's done is the grain is thrown against a mass sensor, really, and it records the impulse, as this happens. And the grain is being thrown very fast as the machine goes through. And there's some sort of averaging that the machine does. But go hit a gopher hole or something like that, or get on an angle, these kinds of things. These are all adding errors to that data that you're measuring. And the thing you're really trying to ascertain is what is the yield. And maybe even more you're trying to ascertain is why is the yield? What's going on? The yield is a measurement that tells me something about the inputs and the soils and these kinds of things. How accurately can we actually do this thing? So that's a role where a university ought to fit in, is to sort of separate a little bit the marketing, which is a necessary thing, from the practice. Are farmers are they able to get statistical significance out of the data they are looking at? Are they able to actually make decisions that are based on, that are defendable, Or are they looking at pretty pictures? So in some cases, they're looking at pretty pictures and they're just happy about it, But that's, of course, not the ultimate goal, and it won't bring enough value to make businesses out of in the long run. So we need to understand our data a lot better. Humans have been using data forever. These are fun. I like the far side. I don't know about you guys. It was one of the saddest things when it was gone. But, whatever, Thagomizer or whatever. Analyzing data helps us to make decisions and take actions. So we should write that spot down, So what has changed since those days, really? Well, there's a lot more data. Machines can collect data, and they can also use data. And we're trying to do a lot more with it. Data is kind of the holy grail. We can collect data from a lot of sources, right? Data science is collecting that data. It's making observations about patterns that might be in it. It might be visualizing trends, similarities between data points, predictions of about what might happen in the future, courses of action, developing new machine learning, accelerating analysis algorithms. So there's also a computational aspect to this. But the whole goal here is really analytics, to be able to predict and to be able to explain. What industries has it impacted? Well, medicine, retail, transportation, education, and agriculture too. So it's only now that people are beginning to realize just how it's impacted agriculture and what its potential to impact agriculture is, but it's definitely there. Okay, so now we've kind of left the reasons why we want to do it. I want to talk a little bit more about Python. It's a general purpose programming language. It's been around quite a while. It uses white space indentations instead of the usual curly brackets to separate out things. I don't expect that there are programmers, many of you in here, but I do also think that this is one of the languages you could learn how to do something with. And so, instead of watching, Breaking Bad for the second time or the third time, maybe do a little Python. Of course, maybe I'll be watching Breaking Bad myself, I don't know. It's pretty darn good. It's really becoming the industry standard for data science, and that's driven a lot by Google, but it does compete with R. I spent a fair bit of the summer working with R, and I must say, I hate R. You know, maybe I will learn to love R, but Python is a lot closer to the things I think, you know. There's a lot of open source libraries, NumPy, Pandas, Matplotlib, and then a whole bunch of control functions for controlling it. And that little bitty code there, I don't suppose you can read, but hopefully in a little bit here we'll have some slightly bigger code. I'll quickly go through these, but what are some data analysis examples in practice? So you have a data set of GPAs, you know, their high school GPA, SAT, the name of the person, the residence they are, and we might want to learn something. These might be applicants to Purdue, say. So we might want to know which students come from which states, what's the distribution of the GPAs, the SAT scores. Do we consider the GPAs in Indiana and Illinois to be equivalent? Do we need to normalize? These are the functions that have to be done in any kind of data analysis that you would do. Then you can visualize it. You could build histograms and think about the bucket sizes of your histogram and so forth. Ultimately, though, we want to reason about the data. We want to know something about how Purdue applicants compare to the national average. Maybe the mean GPA of applicants is 3.6. Is this big or small? Is it a sample from all high school students? What if we get a sample like that that's only got 1,000 GPAs and has a mean of 3.4? Does this really mean that Purdue students, on the average, have a higher incoming GPA than most students do? I hope so, maybe, but I don't know for sure. Depends on, you can't answer that question with the information here, can you? What's needed to answer that question? The mere mean difference. So this is one of the first things that people screw up constantly. It's like, okay, the Purdue mean of applicants is 3.6, and the mean of all of the high school students out there of 1,000 GPAs that we sampled is 3.4. What do I need to know if that means anything? You have to know the variation, right? I have to know what's the variability. Is this a random chance that this statistic calculated would just happen to be below Purdue's mean? Or is it statistically significant? Is the probability of that happening small so that it means something? That's the whole game, really, when it comes to analyzing data, are you looking at statistically significant things? Also, the sampling method could be unbiased. You need to know confidence intervals and things like that. Maybe I want to make predictions. Maybe I want to do some sort of least squares thing where I'm able to look at various factors of a Purdue admit and decide this person is going to be successful or not. And then, based upon my prediction of that, I admit them. Probably based upon how much their mom or dad gave to Purdue. Although, you'll notice that it's rather one nice and amusing thing. It's both happy and sad, is that there was no scandal about getting into Purdue. So no movie stars wanted to bribe anybody to get into Purdue. Okay. I think that's good, probably, but also a little sad. Yeah. Okay, maybe we want to do things like classification on whether these are going to be good students or bad students, or maybe we want to do clustering. Maybe we want to estimate more than just admit or non-admit. We want to estimate whether it's an A student, a B student, or a C student, that sort of thing. Have a little finer thing. So all of these kinds of things we need to code to be able to answer them. And so one of the main programming languages is Python. So let's talk a little bit about coding in Python. And this, again, my reason for doing Python is because I can't do MATLAB up here. I have MATLAB, but the other problem with MATLAB is you can't take my MATLAB and run it unless your company's going to spend $100,000. So it's essentially useless, at least as code. It's okay you can read it and figure out algorithms. But I really should be releasing this stuff in Python or something like that. So the reason I do it is that. It's not that I particularly love it. It's not even that I'm particularly good at it. I'm probably better at MATLAB, more time to get addicted. But there are various tools in Python that are really useful, like this Jupyter Notebook. This allows you to get your feet wet, to play around, to see what the variables do without really knowing very much. And also without having, it kind of works cross-platform on many systems. That's another big important thing. So there's basic things that I probably gloss over because I suspect most of you haven't programmed enough to know that no declaration command even matters because you didn't know there was. Is that true? I mean, nobody ever heard of the declaration command, or did you? How many heard of it? Thanks, Aaron. Thanks, Andres. So a few of you have. So a few of you have you have to have a programming course to have ever seen that. So the thing is that Python actually allows you to declare it when the variable is created. The variable is actually created when a value is assigned to it. So it's very flexible. It means I can change that variable anytime I want to something else. Okay, totally flexible. This is both a benefit and a curse. Okay. In addition, there's few rules on naming. Some programming languages have a lot of rules on naming variables. This one's very flexible on that. It's case sensitive, so little Purdue and big Purdue are different variables. It does all kinds of crazy combinations. It'll add numbers together, it'll add strings together. So that's what that shows. It has the usual control type statements, logical statements about variables, if, and else statements, while loops, for loops. It can break and it continue out of a loop. I'll give you examples of all this. It has a number of data types. Lists are one of the 4 collection data types. That word really just means kind of set. Although since they called one of the data types set, they don't want to use that word there. Okay, so in addition to lists, there's something called tuples, sets, and dictionaries. Lists are ordered, they're changeable, and they allow duplicate members. So the one list that's listed there is apple, banana, apple, and cherry. You can have repetitions in a list. You can pass an index integer to it or a range of indices and address those various things. So this list of 0 is apple. It's that string apple. You can look at the length of things, like the length of the list. You can append to a list. You can add things to it. So kumquat, if you want to put that in the list, you can go this list.append kumquat. Removing items from the list and other various shorthands. These shorthands are quite useful. You can use lists in for loops. So a lot of languages, like if you're an old Fortran programmer, how many have heard of Fortran? It's a little better. That's what I learned Pascal and then I learned Fortran in order to really do something, but that's been a long time. In those, you would iterate over integers, in a list, not over the words in a list or string or things like that. So Python has the ability to do that, and it's a very flexible thing to be able to do, and it shows you this here. You can use lists to index into other lists. You can write functions, which are just blocks of code that run when called. It's a kind of modular way to separate your code out in order to, well, if you just write it all in one big old file, you're going to find that very difficult to debug, and you're going to find it very difficult to even do it because you've got to solve all the problems at once. That's what functions are useful for. You say, I need a thing that does this. I'm really not sure how to do it. I'll put it in my code right here. Later, I'll maybe figure it out. You can pass parameters to functions and so forth. We got another data type called a tuple. They're unchangeable, and they allow duplicate members. So once you made a tuple, you can't ever change it, and that's useful in some cases if you want something to not be changeable. There's things called sets. You don't have duplicates in sets. So sets don't have order, and since they don't have order, it wouldn't make sense to have duplicates in them. You can add to sets. You can do set operations on sets like unions and intersections and things of that nature that would be very, very hard to code in Fortran. And then there's things called dictionaries, which are unordered, changeable, and indexed. They also look like sets with the curly brackets, but they're key value pairs. So they have a key and a value for that, like brand, Ford, model, Mustang, year, 1964, and so on. You can do a variety of things with that. Now, I have a little time left, so I'm going to switch over to the Jupyter Notebook and actually go through some of these things with actual code. And then tomorrow we'll do some more of it if any of you show up. I hope you do. But are there any questions about that so far? Okay. Now this is the part I'm a little worried about in the sense that I'm not sure how easy it will be to see. So if you want and you want to see, can you see okay? He's really good eyes back there. Okay, I'll believe you. Okay. When I'm done, I haven't done it yet, but I will put this on my GitHub. There isn't a whole lot on my GitHub. Aaron knows that. But I will put this there, and then you can take it and use it. It's the only real value is learning Python. But, you know, I don't really think you can learn it by me just spewing this at you. You learn by doing in all things. If it's important enough to you, you will. This is fairly easy to do. Okay, so that's the outline of topics in it. Let's start out with that first notion about basic variables. So we talked about dynamic typing. So a Jupyter Notebook, what it does here is I run this, I hit the run key here, and it'll execute this section of code right here and put the result down below. Okay, so I've cleared it all out, so we have to execute it in real time here so you can see it happen. The top stuff on the top is what's called a comment. So you indicate that with that hash symbol. It does not execute anything for that, and so you can use that to explain what you're trying to do. So I've tried to be liberal in my use of comments. That's a very good programming practice in general, to explain why you do what you do, because real projects need more than one person to solve them. And so this is a way of communicating with other developers. Okay, a Python variable is more than just its value. We know that already because we can change its value over types at will. We can have it be an integer, we can have it be a string, we just assign it a new value, it gets a new value, the name's the same. There is overhead associated with such flexibility. This is why you wouldn't have necessarily, why they didn't want to do this in C or in Fortran, because it was, well, first of all, there was not really the technology, I don't think, at the time to have built compilers or ways to implement these things that would have worked. But they don't run as fast. So you have to do some special things in Python to make it run fast enough to handle big data. And so that's one of the things we'll have to kind of look at here. In this case right here, in this little code snippet, I have x equals 4. I print the type of x, then I print x itself, and then I follow it with a reassignment of x to the string 4. I print the type of that, and I print the variable, and then I run it. Okay? Oh, I wasn't in the right spot to run it. There. I'm going to run it here. Okay. So the first one, x equals 4, is of class integer. And when I print it, I get 4. And the string 4 is of class string. So that's stored a different way. Later, I'm going to show you how much space it takes to store these things. So you'll see some things going on here that Python is doing in the background that influence its efficiency. And it's really critically important that a person ultimately understand that if you're going to write code that's more complicated than anything I'm doing here. Okay, but we'll leave that for the moment. In the collection data types, there are 4 of them: lists, tuples, sets, and dictionaries. We've talked about that already. I started out here by defining a list, and I called it Colorado things. And I put in it wheat, corn, sugar beets, pinto beans in 1959. Does anybody know why I picked those things? I live in Colorado. I grow wheat. I grow corn. I used to grow sugar beets. Thank God I don't anymore. Used to grow pinto beans. Do miss them. And I've lived in Colorado. Well, I don't live in Colorado now, but I started living in Colorado in a year that many of you, your parents weren't born. So there you have it. I ask it then, print the type of Colorado things. It says list. Then I say print the length of Colorado things, 5. Then I say print Colorado things, so it happily prints them for me. It doesn't care, by the way, if it's a single quote or a double quote for a string. It's happy enough with either one. I reference a particular Colorado thing, the third Colorado thing in the list, starting from 0. So wheat is 0, corn is 1, sugar beets is 2, pinto beans is the third thing in the list, and so it prints pinto beans. I ask it about this thing, pinto beans. What is it? It's not a list, it's a string, so it tells me it's a string. I ask it about 1959, or ask it about the fourth thing in Colorado things. It's an integer. So that's one of the first things you observe here is a list can be made up of non-alike things. Integers and strings and booleans and so forth. Booleans are things that keep track of they're true-false, essentially. They're 1-0 things. They tell you the outcome of a single question asked, which, of course, at its base, even though it's Python, you're still programming it because it's still as dumb as any computer ever was dumb, right? So it still comes down to binary questions. Let's move on, and we can append to a list and insert in a list. So I'm going to run that. I appended to that list something called Amherst. Then I printed it, and I got the whole thing printed out there. I then inserted something else. So I appended Amherst. It put it on the end of the list. I can insert in the middle of the list with the command with a 2 here. I put sunflowers in there, and so sunflowers appears after the second, in this place of the second. And the list just gets longer and longer as I do that. Now let's leave lists and let's talk about tuples. Tuples are ordered, unchangeable, and allow duplicate members. So let's start out with Indiana things. I'll put basketball in it. But if I don't put a comma behind it, so there's a few little weird things that you need to know about a programming language, and this is one of them. If I just assign it like that as a string, it's going to make a string. It's not going to make a list. If I put a comma behind it, it'll make me a list. And so you can see that when I print the type of Indiana things at the first command, it tells me string. I then add the comma, run it again. It tells me tuple. Okay. Then I redefine it. I just add another thing to it. Okay. So it's happy enough to do that. You know, you can always just redefine it. Now I have two things. I have basketball and corn in that thing, and so forth. One thing is they're unchangeable. Okay, so I did mention that. Now this looks like I changed it, right? Well, I redefined it completely. So let's try to change it. You need to get used to things that break too. So I'll uncomment that. See if I can run it. Now I'll run it. I'm trying to append to Indiana the word Wall Street into Indiana things. Now we know that can't work, right? It's got to be broken because Wall Street sure as hell not in Indiana, right? So let's see what happens. Oh, there's an error. Okay, so the error is tuple object has no attribute append. So this is really the point I was making, that tuples are unchangeable. So when you try to append something to it, it's got to complain, and that's the way it complains. Many times the sorts of complaints you get are hard to figure out. You know, that's one of the values of something like Jupyter. You can experiment and see what line breaks, you know. There are other ways of doing that that are probably better. I'm going to uncomment that again to get rid of it, and then run it again, and now it's happy enough, okay? So sets, let's do sets. How am I doing on time? 5 minutes, right? Something like that. What time do you start? Well, I'll find a good spot here. How are people? Oh, am I 3:20? Oh, good. Then I'll just keep going. And then you start after that, Aaron? Andrew? Okay, we won't stop too quick. So there's sets. They're unordered. They're changeable in the sense that you can add and remove items from sets. Does not allow duplicates. So if we tried to duplicate, certainly we should get an error. Okay, so I come up with Purdue things. What are some Purdue things? In this definition here, I've got OATS, I've got IsoBlue, I have students, professors, Gene Katie, and study sessions. Okay, I'm going to print the type of Purdue things, and then print Purdue things by just printing the whole thing, and then I'll print it with a for loop where I iterate through the things in Purdue things and print the thing. So that's for X in Purdue things, print the thing. And then I'll lastly run a command which checks to see if OATS is in Purdue things. So let's see what happens when I run this. Okay, first of all, I said, let's print the type of Purdue things. It says the class is set. And I say print Purdue things, and it prints them all. Notice one thing. I'm actually not sure of the order it picks, but it does not necessarily print it in the order I put it in. So Python has a way of deciding what the order is to go through here, and I'm not quite sure what the order is. I'm sure there's some rule that makes sense here. Aaron's ciphering that rule right now probably, or knows it. I don't. But at any rate. Then, though, if I go for X in Purdue things, it actually prints them one at a time on their own line. So I started out with Gene Katie, study sessions, professors, OATS, students, ISO blue, and the last command here is the prints. Is OATS in Purdue things? So that, what's in the argument there is actually a test. Is the string OATS found in Purdue things? If so, it's true, and it would return true. If not, it's false. So if I misspell OATS, it'll come back false. I spelled OATS right, so it comes back true. This is one of the ways you test and then execute a different way, a different path in the code, depending upon the outcome of that test. All right, now, since we're at Purdue, let's ask the question about IU things. I need to preface this with the fact that Purdue and IU are bitter enemies, or rivals, I think. It's probably fair. So what things do we have in IU things? And of course, a Purdue guy wrote this. It's a little unfair to the IU people. But IU things are Hoosiers, Bobby Knight and Gene Katie. Does anybody know what the deal is there? Who threw the chair? Bobby Knight. Students, professors, and parties. Parties. That's what IU has. So now I'm going to, and so I'm going to print Purdue things union IU things. Okay, that's the first thing. Well, first I guess I print, the union of them. So parties, Gene Katie, study sessions, Bobby Knight, professors, OATS, students, ISO blue, and Hoosiers. That's everything that's in both sets. That's the union. Then I printed next IU things, Purdue dot intersection of IU things. So the things that's in both sets. Again, this is a very useful thing to be able to do in a programming language, because that's a hard thing to implement if you're talking integers and stuff and floats. Thank God for something like this, right? So the thing that's in the intersection of them is just students and professors. No study sessions at IU, no parties at Purdue. Okay. IU things difference, Purdue things. Parties, Bobby Knight, and Hoosiers. Is Gene Cernan a subset of Purdue things? False. Uh-oh. Better add Gene Cernan to Purdue things and then ask the question again. True. Does anyone know who Gene Cernan is? Astronaut. He's an astronaut. He's the most recent man, or he's passed away now, but he was an electrical and computer engineering grad at Purdue. So the first man to walk on the moon was Armstrong. And the most recent, Cernan hated the word last man on the moon, but he was the last man on the moon so far. But he hated that, so in his honor, I guess I'll say most recent man to walk on the moon. Okay, now moving on, we've got dictionaries. Let's look at an example of a dictionary. Dictionaries are unordered, changeable, and indexed. They're written with squigglies, but they're made up of key-value pairs. So one way I might do this is I might have this dictionary here. Old Combine, brand is Case, model is 7130, year is 2014. New Combine, brand is Case, model is 8240, year is 2016. Tractor 1, brand is Case, model is 290, year is 2013. Well, you can see what Krogmeyer's farm with. Pickup, brand is Chevy, model is Silverado, year is 2005. Must not be doing all that good because that pickup is quite rusted out, but it's the one I drive. And then favorite old combine ever, brand is John Deere, model is 7720, year was 1978, color was green. Print type, favorite combine ever, class was dictionary, and it gives you the outputs of this thing. And then print type is class dictionary, then print the whole thing. It prints it out here as these key value pairs separated by commas. I like red combines a lot, but that was a very good combine, that 7720. You can create dictionaries of dictionaries. So I can call something farm equipment and just adding them together. A C1 for old combine, C2 for the next combine, and so forth. It just keeps conglomerating them together. So you can build interesting data sets out of things like that. Then control statements to see how you would change things. So here's an if statement. A is 1, B is 1. These are setting them. They're both integers. Then I go through this chain of things. If B is greater than A, print B is greater than A. If A equals B, print A and B are equal. Else print A is greater than B. It turns out since A equals 1 and B equals 1 that A and B are equal. Just to be sure that it works, we'll change it to 2. We'll run it again, and B is greater than A. So you can do while loops. While loop, what it does is, it's, at least in this case, starts with an integer value. It's going to increment that integer and print it each time. When eventually the integer gets too big, it'll fall out of the loop and it'll stop executing. So let's see what it does here. Prints 1, 2, 3, 4, 5. How nice. As we know, we can iterate through strings and lists and things like that. So we could start with banana. For every x in banana, print x. And then maybe we try something else. We'll try to break the loop with the continue command by putting an if statement. So here for x in banana, if x happens to be an n, we'll continue. Continue means don't execute that command, but continue the loop. So what it ought to do is, it ought to print banana for the first one, and then it ought to print ba for the second one because it left all the n's out. Okay. All right, now you've gotten to the spot where you want to do something more. Okay, so we'll talk a little bit about that. We're doing fine. Any questions so far? Do you think you could do this? Good. So this comes down to some of the issues that a language like Python has. That its flexibility is like its Achilles heel at the same time. And so because of that, and because it's an open source project and people are desperate out there to come up with solutions that solve the MATLAB problem, communities of developers have developed packages that can run faster. So one of them is called NumPy. So all data that's manipulated in a computer is really a binary. It's represented in binary. So none of this stuff has changed any of that. Okay? In other words, one way or another, all data, no matter what it is, sensor readings, pressure readings, an audio file, images, a yield map, they're all arrays of numbers one way or the other. And they may look like strings and things here and there that are helpful to us for manipulating them, but by God, they're numbers. Okay? As it turns out, you need if you're going to try to do computations on these things, there is overhead associated with how you store them, and very flexible languages have a lot of overhead. And so the mechanisms that Python natively gives you, like lists, that you could use to represent arrays of integers or floating point numbers, those have a lot of overhead associated with them because you're allowed to change a number in the middle of the list and change its type even. You know, if you weren't allowed to do that, they could store it more efficiently, and they could compute on it more efficiently because they don't have to check, is it a string or is it an integer or a float every time. Every time you put something in a loop that has to be checked every time, and you don't really think of that as checking, that sometimes way slows down a program. So we import NumPy, and Python does this all the time. Nobody likes to type NumPy and the command. So they tend to give shorthands. So the common one for NumPy is NP. I think I could call that anything I want. I could call it Aaron if I wanted. If we wanted to know something about documentation of NumPy, there is a shorthand. You can just put a question mark behind it and run it, and it'll produce for you the documentation having to do with that NumPy. I'm going to get rid of it, though. So let's think about the numbers that we're storing in the computer to start with. So this is really getting at how efficient is Python at storing numbers. Okay? So this is a little bit of electrical engineering or computer engineering that has to do with how numbers are really stored in a computer. So a C integer is a label for a position in memory, and the bytes in that memory, in that position, encode the integer value in some way, like a binary number. So you've probably seen base 10 arithmetic. That's the stuff, I guess, we all grew up with, right? But there, you can do base 2 arithmetic, right? And you could do all the computations that way. So you can encode a number that way as a base 2 number. So 1010001111. Or you can code a number as a hex number. So then I've got the values 0, 1 up to F, right? Those represent the numbers from 0 to 15 in each digit. So there's a variety of ways you can do this. Okay? Ultimately, though, this thing has to be, a Python integer is a label. So that's what a C integer is. A C is very efficient in the way it stores it. Python instead, because it wants to allow you to change it later, it's actually a label for a position in memory that contains something called a C structure that contains the Python object information, including the bytes that encode the integer value. So it encodes all kinds of stuff about it so that you can change it from an integer to a float, to a string, to a list, or to anything you want. So let's start out with the integer 1. So we import sys. Sys is a package that allows me to monitor some things about the implementation here. So I'm going to define an integer 1. I'm going to print it. I'll print its type. And then I'll print sys.getSize of that thing. So that returns the number of bytes needed to encode the object. So when I run that, one thing you'll see here is, okay, it's 1. It's the integer 1. Its class is integer, but it takes 28 bytes to encode that integer. So that's actually quite a few bytes to encode an integer, right? Then I run for the 1 as a string instead of as an integer. I run it. Same thing, I get 1 when I print it. Its class is string, but it takes 50 bytes to encode that. Now let's look at L equals 1,000. So will going from L equals 1 to L equals 1,000, both as integers, make a lot of difference in the size that it needs. It already needs a lot of size, so it's already got a lot of overhead. Let's run that. I'll be darned, it's exactly the same size, So in other words, the encoding of that integer, even though the integer got bigger, it fits in the size, really, that fits in the computer anyway. If I put a big enough integer in there, I can start to make that bigger. But it's very good at storing integers. It has a lot of overhead with it, though. Now let's look at L equals 1,000, the string. And that takes 53 bytes. So it actually, now that string is longer, and it really needs more memory space for that, because now it's an array of things. Okay, we can look at lists. I'm going to kind of run through these fast. So you can look at lists. So a list of the first 10 integers here takes 216 bytes to store it. A string, so this str of C for C and L1, what this does is creates a string of values that are 0, 1, 2, 3, but they're the strings, not the integers. So let's run it and see what it does. There's the thing it creates. It's a list. The things in it are strings. And now it takes 200 bytes to encode that. And then we can do even more things. We can make things that have Boolean things in them as well. So that's why a list is a very flexible structure. We run it, and we get the same kind of thing here. Okay, so there's this way overdoing it on the minimum amount of space that you would need. You'll also see this. There's other commands in Python that allow you to compute how long it takes to run something. And you'll see that, with these sorts of data types, they sometimes are very slow to run. NumPy is a method to solve that, as long as you can tolerate the idea that your list is really all integers or is really all floating point. They're really numbers, and we won't allow them to be strings. We compare a Python list and a Python array. So I'll run that here. So I import this thing called array, which is a method that Python has. I create one. I print it, and print its size and type. And then I just print the list itself, okay? Where list here, well, you'll see what it is when I run it here. We'll see what it does here. So the first one here, which is A, is this array, and it labels its type integer, and it's this array of integers. And its class is called array.array. And it takes 464 bytes to encode it. When I put it in a Python list, just L, and do the same thing, now it's encoding integers, but it takes 1,016 bytes to encode it. So Python was trying to get at a more efficient way of encoding because they came up with this structure called array. All right, and it's definitely more efficient. It's essentially got the same information in it that I want. One is half as big as the other one. So you have to pick the right thing when you're doing when you're setting up your program. Going beyond that, there's something called NumPy. So NumPy also adds to this capability of efficient storage, efficient computation, MATLAB-style computation, where you're able to index into an array with things they call slicing. And it really is a way of effectively making it very fast. Rather than running for loops to iterate through the things in a big list or an array, well, there's a for loop you do, but it really runs at the most basic level of the computer. So it works better for the runtime compiler. Anyway, we'll run that. All right, so that's well, in there you see the result of it. You've got a particular item size in each one of these. These are called numpy.nd arrays. We'll start to use them here in a little bit because this is the way you actually want to compute on something. I want to now turn a little bit to visualization. So one of the other big advantages of MATLAB is the idea that you can plot very nicely and very simply. MATLAB has wonderful plots in it. So people, I don't think Python's plotting is quite as good as MATLAB's plotting, but people are, and this again is an example of open source, there's communities out there of people with apparently nothing better to do. Or, I don't know, they all work for Google. Google's a wonderful place. I don't know if you've ever visited there, but I did once. Did you come with me to Google? Yeah. Well, it's the most amazing thing. I mean, they've got beach volleyball out in the thing. Everybody's playing. They're all young. I mean, I go in there and they're like, "What's Grandpa doing?" But they got people there to do their laundry and to watch their dog and all of this kind of stuff. And so I suppose there's time to work on Python too. They got all the food you can eat, And you see all these young people. They're all like 20, and they're all there bellying up to the trough, piled high. And all I remember when I was sitting there was this evil, evil thought I had, which was like, you'll see. You'll see. Anyway, so a lot of them are making us MATLAB. Here I am insulting them while they make me this wonderful plotting routine. So matplotlib. Let's run that, and then let's check what variables we have so far. So this little command who goes and looks and says, oh, what's been defined already? And so it gives me my names that are all defined. I'll make an array here, a numpy array, and that'll add a variable to my list here. Now I've got an x and a y. Because x was defined before, I redefined it here, and then I added a y to it so it appears in there. Now in order to do these plots, I need to import this package called matplotlib. So that's one thing you'll find, and then it gives me the version of it here. You've got to kind of keep track of that sort of thing. You want to keep your versions up to date and stuff like that. I'll import matplotlib.pyplot, and since I don't want to type that every time, I'll call it PLT. And then I'll ask it, what plot styles do you have available, at least the first 10? And it'll give me this. That's what that command does. And how do I figure out these things? Well, I have one good book on Python, but mostly what do? You Google. You just Google. This is the thing I still can't get over, to be honest with you. It's like, you don't go to a book to learn this stuff. But I need a book. I learned on books. I had a Pascal book, and then I had a Fortran book, and I read the book, and then I programmed, but you can't do that now. So, you get a little bit familiar with it, but then you start to Google. That's kind of the story here. So plot styles are this classic test, something called BMH, classic, dark background, fast, 538. I think that refers to Nate Silver. ggplot, grayscale, and so forth. I'm classic, I'm old-fashioned, I'll pick classic in my plots. So we've defined an X and we defined a Y, and now we want to plot them, one against the other. So I'll go down here and I'll run that. I ran that again. Now I'll run print X. So X is these integer indices here, 1 through 10. I'll run it again. Now I've got Y, and now I want to plot X versus Y using the classic style. And I have this command right here that does this. And there's the plot. You can label the plot. You can put a grid on the plot with various commands like this. Okay? Maybe I want to do another one. So I'm going to now define X to be all the 100 values between 0 and 10. Okay, so these will be floats. I'm going to plot now another figure using the classic style, but instead I'm going to plot X versus its sine and X versus its cosine on the same plot axis. And there you go. There's the thing. Anybody remember the sine function and the cosine function? And if you're an electrical engineer, this is the thing you grew up on. It's all about phasors and sine waves and such. Maybe, though, you're more of a statistician and you're more into random things. So NumPy also has random number generators. So I define X to be random normal. So rand_n is the normal or Gaussian distribution with 0 mean and variance 1. I'll draw Y as well. If I draw one random vector after another random vector, they are independent as far as random number generators ever are independent. So these would be independent random numbers. I'll then plot the histogram of what the scatter plot looks of the X and Y pairs using this command. Plot histogram 2D, X and Y, give me 30 bins, make me a map, make me a color-coded map with blues. And you get something that looks like this. So you can see that, in fact, the distribution it's peaked in the center. It's basically symmetric. You know, does anybody remember what the Gaussian distribution looks like in one dimension? It's the old bell curve. Looks like that. When you have two independent Gaussians, one in the X direction, one in the Y direction, you really have the cross product of two bell curves, which is sort of really a bell. It's a two-dimensional bell in that case. It's easier to look at it here as a histogram. This is a histogram where the height of the bin is represented by the color that we use. Okay, so now that's the problem with this then is, of course, well, what now? We now need another package. How am I doing there, Andrew? Okay. So I'll stop here at pandas. So pandas is a way to build other things useful for data science on top of NumPy, because NumPy is basically arrays of numbers. But if you're familiar with R, and you've done any R, you know that the basic data type they like is called the data frame, which is essentially an Excel spreadsheet. Now we're talking, right? It's got column labels, it's got row labels, it's got data in the columns. The data may be different. That structure in Python is called a pandas structure. And so pandas is written on top of NumPy to allow us to do computations on that thing called a data frame efficiently. And so I will do that next time.